I'll
All
mention
right.
it.
Welcome,
Thank you.
Richard. How are you doing today?
I'm good. I'm good. It's
So,
I liked.
go
Go
ahead.
ahead. No, I liked Paul's background. I've got my kitchen as my background.
Yeah, it's trickstery, and I think all of us are going to become video producers in the coming months as we try and top one another one telecon at a time. This is how we do things now, it appears. Um, so I am so sad I don't get to hear your talk in person, and so very grateful you've agreed to come on and talk to us here because this is research that I've been following online because it's super cool. I just need to finish cropping your slides so that they appear on screen. So can you tell our audience while I set up your slides just a little bit? Um, where are you now?
I had plans to be traveling, but of course to India and to the obviously the Lunar and Planetary Science Conference, and then shortly off to Russia and Siberia. But I am in my kitchen in Ottawa, Canada.
Well, we have a rich with Canadians audience. So I
Okay,
think
good.
you're in the right place. All right, so I'm gonna go ahead, um, click a box that will hopefully get rid of there. So your slides are now up on screen, and you just need to tell me when to advance the next one. And please tell us more about the awesome sauce that is the underappreciated world of Venus.
Yeah, will I see the slides then as well on the screen? I was watching Paul's presentation, so that was obviously easy to see where things were at. Or
Um,
should I run it in
let
parallel here?
uh, let me see if I can share my Wirecast with you. One moment, everyone. I'm gonna try not to blow up the planet. Um, no, Zoom is currently
Okay.
having difficulties and said no.
Okay.
Um,
I will just pop mine up in the corner so I know where I'm at, and then I
okay,
can.
that sounds great.
Okay. So I'm on slide one, and
Yep.
I'm very pleased to be following Paul in his presentation. He gave us a wonderful overview of Venus and all the wonders of Venus, and so we are actually collaborating on some of these different aspects. So it's been a kind of it'll be kind of a good 1-2 sort of story. My focus is going to be a lot on then the using the geology of Venus to try and understand something about this global warming story. Next slide. Okay, and I'll move myself. So this is based on several of the Lunar and Planetary Science Conference abstracts. The two in pink or in pink box there are the ones that it's most linked to, but it's also linked to the work of Paul and Richard Gale and colleagues, and then also on the this impressive story of looking at the layering on in some of the tessera, the lineament patterns, and saying, "Whoa, these could be just like on Earth. These could be just like sedimentary basins on Earth. These could be just like volcanic sequences." And then as well, some volcanic mapping that I'll show a little later from my one of my students, McClellan. A lot of this is work based on my student Sarah Kawaja, who's finishing her master's thesis. Next. So Venus is cool, hot, 450 degrees Celsius, amazingly, self-cleaning oven, as Paul said, high surface pressures of like 90 times the density of the atmosphere as Earth, 96% CO2. Such temperatures, no free water, no surface erosion, and incidentally, no plate tectonics, which is such an important part of Earth's geology. But it does have, as I'll show later, immense amounts of mafic volcanism. Volcanism is the story of much of Venus. And as you see on the right side there, you see these rift systems, these in red. You see the green areas, which are individual volcanoes that are up to 500 kilometers apart. I guess that's about 300 miles or so. So In Canada, that would be something like the distance between Montreal and Toronto, a single volcano. And then there's a whole bunch of other features, these circular things called corona, which are also volcanic. And then much of the rest of it is either tessera, a few percent, 8% or so, and volcanic plains. And we'll look at some of those different aspects as we go along. Venus is currently totally bizarrely hot. But some of the climate modeling of recent years says Venus may have been Earth-like in its conditions for most of its history. And so it likely had free water, it may have had plate tectonics, and then something happened and we lost that style on Venus. So Venus was Earth-like, and then it stopped being Earth-like. And maybe around 700 million years ago, which is sort of the time of this massive amount of volcanism and massive CO2 release. And so this is an example of absolutely chaotic, catastrophic global warming with no brakes. On Earth, CO2 from volcanism goes into the atmosphere, but then it also gets eroded through erosion processes, and the CO2 gets bound up in minerals. So CO2 is kind of washed out of the atmosphere through normal geological processes. Venus, it's not happening. Venus is too hot seemingly for any water cycle and erosion, and so the CO2 just built up. Next. And so what we're going to look at here is, can we find evidence for this climatic transition from amazingly normal Earth-like conditions to this present self-cleaning oven temperature sort of conditions? And we're going to look at sort of three or several areas. We're going to look at the tessera terrain, which are the stratigraphically oldest things. And Paul was mentioning in his prior talk some of the evidence for erosion and exposure of sedimentary sequences or volcanic sequence. And we're going to be talking about, and he talked about the role of wind erosion. We're going to talk about some evidence related to fluvial erosion from river systems that may have been present at that time. And then we're going to look at, again, the other side of things, the more recent times where we have post-warming and no erosion. And then we're going to look at this critical time between the two and looking and see if we can capture the transition from Earth-like and erosion to not Earth-like and no erosion. And then we'll have this sort of fun little thing about could Earth's future be Venus-like? Next. Okay, so if you look on the right side there, you see this sort of image of, or something got a little misplaced there, but pre-global warming prior to 700 million years ago when conditions say Earth-like. And then this is a broad age range here, but notionally around 700 to 1,000 million years ago, the climate seems to have started transitioning to the present hyper-warm conditions. We don't know whether it's a smooth increase or a catastrophic increase in temperature. That hopefully we'll sort out over time from studying the geology. On the left side, you can see the tessera terrain, where you can see, which are these complex radar bright with complex structures, lineament structures, etc. And the notion is they should be pre-warming. So if anything is showing us, is preserving any evidence of erosion, of water erosion, that's where we need to look. And then on the other side of things, at the youngest time, we have individual volcanoes and flow fields, patterns of lava flows after lava flows, and those exhibit no erosion. Lava flows simply superimpose on one another. And we're going to also get to this middle time where it's the early plains basalts and something called intratessera plains, and we're going to talk about them as potentially capturing the transition. Next. So first we're going to look at this oldest time, these tessera, which are the stratigraphically oldest and really complex and poorly understood. And we're going to see about the evidence for any kind of water erosion. And this is work then, as I mentioned, that my master's student, Sarah Kawaja, is taking the lead on. So one of the things about Venus, the Magellan data is magnificent. This is Magellan radar data that is our best record of Venus, 98% coverage. It's a remarkable data set with about 100-meter resolution. So it's, vertical horizontal resolution. On the other hand, the topography is not so well constrained. 50 to 100-meter vertical resolution and footprints of 10 to 20 kilometers. So it's not very high resolution. There are some processed data sets that are better than that. But most of the planet has that sort of really poor, beautiful kind of image resolution, radar image resolution, but poor topographic. And so if we're trying to figure out whether we have erosion, we'd be kind of looking for river valleys. But because of the topography so poorly known and through the topographic, through the laser ranging that give the topography, we offer a kind of trick to try and figure out what are the low areas. And our trick is based on, if you look at the left image there, you see Salus Tessera, the small little, fascinating little tessera area, surrounded by radar darker things, and those are basaltic volcanic plains. And you see they're fairly flat. And one of the neat things is, when you look at the margins of the tessera, you can see the volcanism of the plains embaying into the tessera. So it's clearly finding for us the low areas of tessera. These are the low areas. These are the old valleys of the tessera that we're going to suggest could be ancient river valleys. So these younger lava flows are mapping them for us. And you can see that schematic idea on the lower right there of the old the plains lavas embaying into the tessera and showing us where the ancient valleys were. Next. And this is just to illustrate kind of a terrestrial analog. So on the upper left, you see the story for the tessera of the darker volcanic plains wiggling into the areas of tessera and showing us where the tessera low points are. On the upper right, you see the same sort of pattern in fjords in eastern Canada. And you can see water following up the fjords and showing us the pattern of kind of ancient river valleys. In the lower left there, you see the same sort of pattern in Greenland. You see ice sheets, glaciers that are filling in around and cutting through the area, and you see these high standing areas called Nunatak. So you see something about the ancient valleys and where the glaciers are. And then the final one on the lower right there is wind. And you can see sort of from the sand pattern and then the structure shaped by wind. The sand area shows you a datum that is horizontal. So this is a really kind of powerful way to kind of look and see the low areas, the valleys, the ancient valleys in tessera. Next. One of the things about traditional interpretations of Venus, of the tessera, is we assume that like present day, the assumption has been no erosion. Just like, the temperatures are too hot. And of course, the initial thing is you say, well, it's probably always been hot. And if it's always been hot and there's no erosion, then in tessera time, there shouldn't be erosion. And that would imply that all the structures we see have to be primary structures without any erosion. And so those structures can be things like folding of rocks. Those can be things like normal faulting, where you have downdrop blocks, as you can see in the image there. You can have thrust faults, where you have one piece of the earth pushed up on top of another, but no erosion. And so it implies some really primary some patterns that we should see in the tessera if there's no erosion. On the other hand, if we have erosion, whether it's wind or glacier or river, we can include all these geological things like folding and faulting and of various types, but then modify it and modify it through erosion, producing, of course, some of the things that was mentioned in Richard's earlier or Paul's earlier presentation, where you could see incised sequences of volcanics. Next. I'm not going to say any more about the wind and glacier erosion. That's I want to focus on the water erosion aspect, but I can certainly address that later if we have time for questions on that. So this is one area of Salis tessera on this one. I think we're on the same slide now. This is the one that says evidence against purely primary. Okay. So you see the tessera there. You see this odd area in the center where you have lava flows that have kind of come up the center of Salis tessera there. Well, what's going on there? If that were a purely geological thing with no erosion, you'd have to imagine it as some sort of fold that was high on the places where you see the white rocks, the tessera, but low, as you see in the central valley there, kind of like the lower image on the right there. On the other hand, and maybe that occurred. There are other kind of geological things that could occur, but you look at the complexity of the thing with all the lineament patterns on it, and you think that can't be the whole story. And so one aspect is to say, well, there's been erosion, that's just a river that's come out from the highlands and eroded a valley, as in the upper right image there. Next. And so one of the things we did was to say, okay, what are kind of river patterns like on Earth? And there are about 6 different kind of types of river valley patterns on Earth, shown on the diagram there, from the river flow literature. And what we thought to do then was to compare these patterns of valleys, terrestrial stream valleys, with the features we see on Venus. Next. And so we looked at various things. So we could say that in the area I was just showing you, you could see you can map out the valley patterns where you see the flooding by the lava flows, and you see a complex pattern of river systems, maybe feeding in from the sides there and then following out the valley. There's another pattern, the radial pattern, that's the second row there. And you can see this sort of radiating distribution of river patterns potentially feeding into a central basin. The third one there is a pattern of parallel rivers, or patterns that look like the lava flows have filled earlier river valleys, parallel river system. And that's a standard type. And if we go to the next slide, oh, actually, that wasn't on the slide. Oh, yeah. And then the next slide, you can see the parallel pattern. And then you can also see a rectangular pattern, a much odd, irregular pattern. So you can see that at first glance, then, it is plausible to look at these partially flooded tessera, flooded by younger lava flows, that the lava flows have shown us where ancient rivers may have been in tessera time, and suggesting that next one of the kind of pièce de résistance here is this one here. So one of the things one sees in river systems is you can see teardrop shaped islands. On Earth, you see one on the upper right there, which is and you see the arrow showing the direction of flow. The lower right is an example from Mars, and here's one potentially from Venus. There's additional things to note on that diagram. We think the later lava flows were coming from the right. And so those, so if the lava flows were responsible for that teardrop shape, then the teardrop should have been the other way. On the other hand, if water erosion is the cause of it, for other reasons, we would want the water coming from the left. And so the teardrop would be consistent with that. Next. So that's kind of an initial story of where we're at with respect to this idea that during tessera time, that may be during the Earth-like time, while erosion was still going on, while there may be even plate tectonics. It's really open at that point. And the other thing it says is that maybe tessera time was a very long time, because one of the things about erosion is it will remove any record of meteorites. And so if there were, and the meteorite record, as Paul mentioned earlier, is how we date things. And so if we only start to preserve any meteorites at the end of the warming time, or at the end of at the beginning of global warming and loss of the water cycle, then tessera time may be really protracted. Now we're going to look at the other end of things. And just to say, let's go next slide. And this is a map. A student of mine has been doing some detailed mapping of lava flows in this Deserto Callistus region. And you can see, complex patterns of lava flows, all in different colors there. On the right, you see, on the lower right, you see this incredible system of lava flows going through a gap in the mountains. You can barely see the gap, the north-south gap in the mountains there, but you can see coming in from the left and then spreading out to the right, different generations of lava flows. These lava flows are just one on top of the other. There's no erosion. And the upper one there, the upper right image, is you've got a feature from which a lava flow is emanating on the left there and moving downslope to the right as this sinuous sort of thing, just superimposed, no erosion. So at this time, which is late in Venus's history, no erosion. All right, well, what about that transition time? Let's look at this transition time. And so we're going to look at two aspects. One is when one looks at the earliest plains, right? This is which is much of Venus. There's widespread areas, a little bit like the mare on the moon, large areas of basalts. And in this area here, this is from mapping a student of mine, Erin Bethel, did mapping a quadrangle, and she did a lot of detailed mapping in the plains and found a number of different subunits. And one of the big questions is, with these plains units, are they pre-global warming? Are they still part of the tessera time? Are they while it's still Earth-like? Or are they already part of the time of Venus's global warming, catastrophic global warming? And so the key thing is going to be looking at the morphology of these different units and to see whether these morphologies, so in this image here, you can see different colors in this, you can see the mapping below and you see the original Magellan image on the top, and then you see the yellow box highlighting a particular area, and you can see in that area a distinction between two areas separated by this dotted line. And the younger unit is within the dotted line. And so can one, when one looks at that pattern, does that look like a lava flow that has just been there and not eroded, or has it been one that's eroded? I don't think we know that yet, but we want to sort of investigate a lot of these early plains areas to see whether we can morphologically distinguish whether they are primary flows which are just superimposing like I showed for the younger volcano, or whether they have potentially emplaced and then had some erosion and others emplaced on top and so on. And so that's work ongoing. Next one. There's another kind of plain. Hello?
Sorry, I think at some point you forgot to tell me to advance the slides. What slide should we be on?
We should be at intratessera plains units now.
There. Okay. Yes.
Were we behind one?
I caught us up. We were fine. I figured out where we were supposed to be in real time.
Okay. Thanks, Lynn. So this other area is the intratessera plains units. As I think Paul mentioned as well, there were areas of these tessera plains that are, complicated, and you see areas in which you've got partial lava flows. You can see these dark areas on the upper left of this image. Those are probably lava flows. They could be sediments also. And one question is, well, what is the nature of them? Well, one of the things, and you can see the lower image, which is also the mapping from Gilmore and Head of the same area, and you can see the gray areas, which are these intratessera plains units. And when you look at them in detail, some of them indeed have little local shield volcanoes from which those flows are probably fed, but some of them don't. And so one of the things we're exploring is whether these could be erosional remnants of much wider lava flow systems that were maybe covering the whole area, and then with erosion, partial erosion, they're only left in the topographically low areas. And whether these might capture an even earlier history than the adjacent plains units. These may be volcanism, plains volcanism, much closer even to the time of the transition from Earth-like conditions to the start of global warming. Next. So here we are back at this story here of saying we've been looking at the tessera, which are by the modeling likely pre-global warming. And in addition to the kind of evidence that Paul was mentioning in his previous talk about wind erosion, we have some candidates for water erosion from the pattern of the valleys that have the lava flows, younger lava flows flooding into the tessera and potentially showing us where ancient river valleys were. And then on the other side, we have the younger global warming, or the time when we're at our present day conditions at the top image there, and incredibly warm and no erosion. And then the middle time is where we're looking to try and capture plains volcanism or intra-tessera plains units to try and capture the transition. The next slide. So one of the things is just, I want to finish with this little uh, wild thought with respect to the future of Earth. On Earth, as Paul mentioned, there are these massive large igneous provinces, LIPS for short. These are huge volcanic events and magmatic events that happen every 20 or 30 million years on Earth. One of the most significant is the Siberian Trap event that produced about 5 million cubic kilometers of rock in a very short time, geologically, a million years. For us, that's a very short time. And it's a time when it caused a mass extinction and where perhaps 90% of life was wiped out. It corresponded to a temperature increase of about 10 to 15 degrees Celsius as well. And there are various other things besides a temperature increase that contributed to its effect of wiping out things. On the right, you see a barcode with the scale is millions of years, so 0, 500, 1,000, and so on, million years. And each of those red lines represents a lip event. There are lots of them. And each of those, many of those, can have a dramatic climatic effect. What we were wondering is, if you look at Venus, basaltic volcanism on Venus is very much like large igneous provinces on Earth. Venus has no plate tectonics, so all the magmatism on Venus must be of the type intraplate, we call, not plate tectonics, but within plate kind of style. And that's what large igneous provinces are. And so while much of Venus thinking has been it's a catastrophic volcanic event that may have caused it, increasingly the time range allowed by the crater counting could allow it all to continue to much younger ages, and we could have then something like a Venus barcode, lip barcode, that resembled that on Earth. And if we're correct about the tessera story of erosion, then there might be a much earlier Venus barcode of events. And so you see from comparing the top and the bottom, I have an Earth lip barcode and I have a hypothetical Venus lip barcode. So if Venus and Earth both started off as Earth-like, what changed to have early Venus become like it is now? Each large igneous province on Earth could potentially produce a 15 degree or so Celsius temperature increase. What if randomly you had several different large igneous provinces all happening at once? So you had a superposition of the temperature increase from each event, from the CO2. You could end up potentially with a runaway thermal effect. And maybe that's the process. We're doing some modeling with colleagues, Michael Way and others, with respect to trying to model this process. But if so, then maybe in some future tens of hundreds of millions of years, as Earth continues to have its pulse of large igneous provinces, maybe we randomly have several of them superimposed of equal scale and in short enough a time that runaway greenhouse warming happens on Earth and Earth ends up like Venus. Thank you.
Wow, that was excellent. So in the parlance of the internet, I totally stan volcanoes. I'm a stalker fan of volcanoes.
Yeah,
And listening to your talk, knowing that you spend part of your year in Siberia, where some of the most amazing volcanoes of the past, if you can call the Siberian Traps volcanoes, are located. Um, I have so many questions. So many questions. And our audience does as well. And I think one of the questions that we all currently have, um, well, there's three. So first of all, is there still? Do we know at all if there's volcanism still on Venus?
Would not definitively, no. There's some suspicion from some of the more recent, some of the
The
missions that there's some volcanic activity, but it's not something we don't know yet. Yeah.
Yeah, there's weird chemicals in
Mhm.
the data from the Japanese probe that maybe.
Yeah. No, I mean Venus is so intriguing, and of course there's so much effort and focus on Mars. Well, that's fine. Mars is super interesting as well, but there are so many unanswered questions with respect to Venus. And one of the neat things is as we're discovering more and more extrasolar planets, there's a lot of interest in extrasolar planets. And that community likes to think of Venus as the extrasolar planet in our solar system, right? And so one of the cool things then is also to sort of look at the relationship between Earth and Venus, otherwise, remarkably similar in, well, position from the sun,
Yeah.
overall composition, size, overall structure, and yet they're so different, have such different climates. And so trying to understand the history of climate on Earth and why the different climate on Venus, especially if Venus started off as Earth-like, is really key to us trying to understand this amazing new data set of extrasolar planets,
Yeah.
some of which are very much like Venus and Earth sign, and trying to understand what kind of populations of atmosphere, what kind of atmospheres are they likely to have, and what does that atmosphere mean, and and so it's a pretty exciting time to try and take this sort of work on Venus and take it to extrasolar planets.
Now with these lips, large igneous processes, was that the P?
Yeah, large igneous, so
Igneous.
igneous meaning magmatic lava flows and their equivalents that are still underground, liquid rock, igneous provinces, as in big regions.
Yes.
I should mention these are huge. One of the things I often say to give a sense of their scale is an individual event. The smallest size we get is 100,000 cubic kilometers, and that would cover all of the US to a few meters, all
And
of the US, all of Canada to a few meters, one of these events. And the biggest one of them would have potentially covered all of Canada or the US to many kilometers, all of it. So these are huge events that, you know,
so this starts to hint at the answer to my next question. Would one of the supervolcanoes, Naples, Yellowstone, cause one of these events if it went off?
no,
Okay.
and in some sense they are smaller scale, right? They're big.
One can hope. I mean,
One of the
we're
things
already
Yellowstone,
facing so many natural disasters. What's a supervolcano among friends?
one of the fun things we're doing though is trying to understand the history of climate change on the Earth, and it turns out large igneous provinces are a big driver of that. What kind of lessons can we get from these periods on the Earth where we've suddenly gone warm and had mass extinctions, or paradoxically, when we've gone remarkably cold? Those large igneous provinces are also linked into snowball Earths, when the Earth has gone into a snowball, when where the oceans have frozen to the equator.
Yeah.
And so we're trying to look at the history of climate change on Earth and get some insights into modern climate change.
And this is one of the frustrations that we have with so much of our data. We can often see what happened and we have no idea why.
Mm.
And in trying to piece things together, there's often multiple paths that all match our data. Now, with your data,
Yes,
looking at,
yes. Well, that's true of Venus and everywhere. That's true. We want more data.
we want more data. We always want more
We want more
data.
data.
Now looking at Venus in the most optimistic of cases, when did it stop having liquid water or something
Well,
else that
I think the argument is somewhere around broadly 700 million years ago, plus or minus at least several hundred million years ago, several hundred million years. So it's not well constrained, but that would be a timing. But it'll be so much clearer if, as we get additional evidence for or against the idea of erosion, water erosion in
Yeah.
tessera, because if you have water erosion in tessera, then that is really diagnostic. That means the conditions for global warming did not happen till after that. And it makes a lot of sense to think of the massive amount of basaltic lavas, basaltic lavas being like the kind we see in Hawaii
Yeah.
and Iceland, those kind of lavas being covering so much of the planet, and the CO2 that they would release, um, is a clear mechanism for the global warming.
Now, I have to say, I may sound slightly like a crazy person, but I'm actually an astrophysicist, which means while I love volcanoes, my background includes no formal training in geology. Um, so the Earth Moon system was created during a massive collision, we believe, which essentially reset our planet about 4 billion years ago in a 5.5 billion year old solar system. Does that mean that Venus is actually older than our world in terms of is done being smashed to bits?
Uh, well, the Earth, the collision happened quite early. I think it was actually, Earth is about 4.5 billion years old. So the timing
Okay.
of all the I like to think of it this way: it's 4, 5, 6, 7 is an easy way to remember the age of the Earth and the solar system. 4, 5, 6, 7, 4,567,000,000 years, plus or minus a couple.
Okay.
And so
So
I'm not, I don't so and the impact with the Mars-sized object that knocked out the moon and
you're right.
reset
That was
things
that was
happened.
4.2 to 4.7 billion years ago.
Yeah, really close. I think within 100 million years of the original of the original formation. So I don't expect there's a major difference between um, Venus and Earth. But of course, one of the things one looks for on planets is we know from the moon that there's a pretty rich meteorite impact history.
Yes.
And we have some stories on Earth. Earth is a very active resurfacing sort of planet, but we still teased out and identified some really major meteorite impacts, back to, well, certainly the one that's near us in Canada, the Sudbury
Yeah.
meteorite impact that's associated with the major ore deposits, and that's what's really been well studied, um, is a meteorite impact at
It's not a
at a,
huge. So the reason I ask is we already had fairly advanced life on Earth by the time at which we're
yes,
discussing
yes,
erosion. A
yes.
fluvial erosion processes were still happening on Venus, which implies there could have been rather significant forms of life. And the reason I ask about is it surface older than our surface is did it have potentially a head start? But it sounds like the answer is nah, with an error, no.
Not really, but it had enough time, as you say. If it was down to 700 million years, that's almost to the Cambrian, Precambrian boundary. So that's where there's a huge blossoming of life at 540 million. So that's about the same. So it could have been quite well developed, and unfortunately, smush the poor Venusians, fried.
And
Yeah,
and I yeah,
no,
it's
yeah,
awesome.
it is, and there probably wouldn't be any way of finding any evidence for that. There are some odd things that are happening in the Venusian atmosphere, and there's a lot of discussion about potential, some potential for life in the Venusian atmosphere, where the temperatures are
Yeah.
much more hospitable. But that's a different story.
But needless to say, the universe is trying to kill all of us all of the time, and it already got Venus.
That's one way to look at it. Yeah, the Venus killed itself, though, in a sense, right?
Well, there's that too. But
That was internal. Yeah,
so
it did it to himself. That was self-inflicted, at least from a planetary perspective.
it's true. The geology of Venus was like, no more. I want nothing to do with this life. You shall die now.
That's right.
Um,
Yeah.
yeah, it's I. My co-host on Astronomy Cast often remarks that I never look more giddy than when I'm discussing the destruction of planets. I may have a problem. But I really love following your research, so I am a fan of your papers and always look forward to them. Um, So what's next? This work is still in process. What are you most looking forward to, especially with? And I'm going to keep bringing this up. The decadal survey is like Venus now.
Yeah.
Um, what's on the horizon for you?
For me, since I'm a part-time professor, a guest professor in Siberia, I'm involved with Helm State University and participate in the conference in Moscow. They're also working up a Venus lander,
Yeah,
um, perhaps in about 8, 10 years. Venera D, it's called, and so NASA's involved in that as well. So they're one of the things that could be going to Venus then at some point is a Venusian lander, and so it's kind of fun to participate with NASA and with Russian
yeah,
colleagues in helping to try and find some landing sites. We would love to land. I'd like to land in one of the old planes units, and
yeah,
you drill down. They as Paul mentioned in the earlier presentation, they've become much better at hardening the electronics so they survive the temperatures better. And now they can potentially think of lasting several hours and be able to drill longer. They were only drilled down a few centimeters in the previous missions, and now they get a big 9 centimeters, which is not so deep, but enough maybe to potentially capture. If you've got the oldest planes units, you could potentially capture some units that were formed while there was erosion going on and
yeah,
then and under ambient conditions, and then they would sit exposed to a super hot, self-cleaning oven temperature for a much longer time. And maybe one would, as one drilled through it and analyzed as you drill down, you might see a chemistry transition where you could see, oh, okay, this is characteristic of the hyperwarming climate. Oh, now we're getting down into the original environment of the basalts, which could be, yes, like the volcanism on land, but it could also be oceanic volcanism, which has its own characteristics. And so I'm kind of excited about that possibility of this lander mission to potentially drill into the surface of Venus in one of these old plains areas and see if we can find evidence for both the
yeah.
present day wickedly hot climate and then the earlier um, Earth-like climate,
One
whether
one of
underwater
my
or not.
one of my fantasies for the far distant future. We don't have the rockets to do this now, but as we get more and more heavy lift vehicles, I would love to see the capacity to take actual core samples that have many meters of
Oh,
sediments to them.
yes.
I would there is no way this is going to happen in the next 40 years.
Yeah, it's going to be
If I'm
tricky.
lucky, I'm going to be in my first robot body that I greatly resent because that is not the future I want, but I don't see how else I could see this happen. But this is the frustration is we would love to be able to go and take these many meter deep samples, and I guess for now the best we can hope for is to see those cutaways that allow us to get essentially a core sample by looking at a cliff face.
Yeah, well, this is a big frontier. Is I think Tessera have been. It's time for a kind of fresh look at Tessera because they're the stratigraphically oldest, and I think we're on to something here of looking at them in much more detail and trying to sort of recognize them in terms of more terrestrial type standard processes. Both of this idea of erosion means that means that they can potentially be much older than the crater counts would give them, and also means that we can use our experience on Earth in different terrains to understand. Oh, okay, that resembles the
Mhm.
stuff we already see on Earth. We don't have to necessarily come with out of this world interpretations. We can come with models that are really well understood on Earth. So that's an exciting area. And then the Magellan data is just magnificent. I mean, there's it is available for people to look at in so much more detail. So there's a lot to be mined from even the Magellan data. Of course, we want a new mission, but
And
this
this is a reminder, the spacecraft may die, but the data goes on forever. We are still finding new things to learn from decades
yes,
old data of objects from
yes,
around our solar system.
yes,
So
indeed, for sure.
I've kept you, and I'm so glad you let me because
This has been enjoyable,
good. Well,
hugely
I hope
enjoyable.
that we can
Thank you.
have you back as you have more results that come
I
out
would
in
love
the
to.
future.
This is a lot of fun, and
So, where can people go if they want to follow your research?
I'm not on Twitter, unfortunately. Let's see. My probably my email and just contact me, or through publications, through my publications is the easiest way. I'm at
That
Carleton University. I have uh, um, a site there, a website that's linked to my name there. So there's some, that's one way. But people that are interested and want to find out more, contact me by email. I'm at Carleton University in Ottawa, Canada, and also in Siberia part of the year.
and have you got where we have multiple people asking, have you gotten to go out and stomp around where the Siberian traps were?
Not in the Siberian traps per se, but one of the things that I work on is we call it the plumbing system. So the magma that makes these big flood basalt piles that where you have lava flows that are several kilometers thick, and it's lava flow after 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 lava flow. I mean,
Yeah.
just an intense amount of lava. That magma has to start 60, 70, 80, 90 kilometers down in the earth. And so how does it get there? One of the things it gets there is through these, we call them dikes. They are sheets of vertical magma. They're coming up in sheets.
Wow.
And so the systems of these sheets that feed the flood basalts, as we call them, those have an immense scale. They have a broad radiating pattern, and they can extend, in some cases, more than 2,000 kilometers, 2,000 kilometers from the center, from the center of activity. 2,000 kilometers. I mean, these are immense things. We see these same features on Venus and Mars. So it's a kind of a characteristic of large igneous provinces, and linked to them being fed from these deep upwellings from the deep mantle. We call them mantle plumes. But I mean, these are, so I work on these systems. And one of the things we've been doing is identifying the large igneous province record where the basalts have been eroded away. And all you're left is with this plumbing system. And so in Siberia, there are several other events of equal scale to the
Yeah.
Siberian Trap event, but are older, are 1.5 billion, 1.75 billion, and so on. But they're equal scale. It's just the basalts have been eroded away. So this history is is pretty impressive. 20 or 30 million
Hmm.
years back for at least the last 2.5 billion years. And
That's
so it's a fun to be discovering more and more of these, and trying to link them, identify their climatic effect, and looking at this. We're trying to integrate the sediment. This is one of the things I'm really excited about, is looking at Earth's volcanic record, lip record,
yeah.
large igneous province record, and integrating it with Earth's sedimentary record. Because the notion is that these big events, like the Siberian Trap event, had mass extinctions, dramatic climate change, and then they also and so that has to show up in the sedimentary record,
Yeah.
and the kinds of things you see in the sedimentary record when the global climate changes. So we're trying to integrate Earth's sedimentary history with Earth's big volcanic history.
It's
So it's
it's
fun. That's really
it's
fun.
it's amazing, and Siberia is a truly beautiful part of this world. I got to go there in, oh man,
Really?
91 to attend
Where'd
the
you go?
cos.
Where'd you go?
I was in Krasnoyarsk for a
Okay.
while, and then I took a. This is going to sound weird, but it was the Soviet Union. There was an elite cosmology school for international students from many different nations that
Ah,
was on an Austrian cruise ship on the Yenisei River. So
okay.
we traveled from Krasnoyarsk all the way up the river until we saw icebergs and turned around. So we crossed the Arctic
Wow.
Circle, and
Wow.
it was an amazing experience that occurred roughly, I want to say it was either the week before or the week after Yeltsin was elected, and 6 weeks before the coup. So it was a different time. But
Yeah. No, that's extraordinary. Krasnoyarsk is only a few hours away, so I've been there a few times. But and I've been up, and well, I've done various expeditions.
yeah,
Earliest was 1994. I flew to Moscow, met somebody at the Yuri Gagarin Monument, and we flew Irkutsk together, and we went up to near the Arctic Ocean, and we spent 3.5 weeks working our way
uh,
downriver. Me, him, and
that's
several Russian colleagues. You know, living off the land to some degree, putting out fish nets every
yeah.
night, and it was an amazing experience, and collecting rocks and
I
surviving.
went on a canoe trip along the Mana River. Take a Geiger counter. There's some radiation issues through there, but
Wow.
it's a beautiful area
Yeah.
to travel. perhaps because it has radiation issues.
Which area is this? Which area is this?
Mana River outside of Krasnoyarsk, Krasnoyarsk 22.
Okay.
They used to do, I don't know if they still do. They were building their RTGs, and from one of the people that I spoke to back then, again, this was 91, instead of doing dual closed system water for cooling their systems, they were simply doing one way through. So they were polluting the local
Oh
waterways
no.
with the outflow from their
Oh
radiation.
my
Yeah,
gosh.
nuclear
Oh my
processing.
gosh.
So I did get radiation poisoning at the age of 17, which is not something I encourage, but it was a truly beautiful trip where we canoed through places that looked like this, constantly changing. Am I in Zion? Am I in
Oh,
Yosemite? It was just
wow.
beautiful.
Well, yeah, yeah. The Krasnoyarsk has a lot of um, climbing kind of climbing areas. People, it's quite
Yes.
well known for that right now. And
Yes.
so,
I actually learned I suck at climbing while there.
yeah, I didn't even try.
Yeah, it was an
Oh, it
amazing
sounds amazing. No,
experience.
I've enjoyed my trips there over the years. I was first there in 1973, so that was a different time. But then I've been
Yeah.
there since about 1990, and almost every year since. So I've
So we may have
seen.
been there at the same
That's
time and
right.
had
We
no
must have been.
idea.
Yeah, I was there 2 weeks after the coup. I went to a Brown Vernadsky Micro Symposium
Wow.
in
Yeah, I studied at the meter in the Caucasus for 7 months, and it was
Mhm.
at the end of that trip that I attended this cosmology school.
Awesome.
So
Sounds
yeah,
awesome. It's good. These are adventures that you never forget about. It's really
no,
it's
and the science community is so small. One of my favorite moments, and then I'll let you go.
oh, this is enjoyable.
When I was an undergrad, I was a summer student at Kitt Peak National Observatory, and I visited Nigel Sharp's office because I was learning all sorts of cool stuff about how to abuse IRAF, which is astronomy data processing software that
Okay.
makes astronomers cry the way ArcGIS makes geophysicists cry.
Okay.
And I saw that he had the same Christmas card that I had from one of the Russian astronomers. And it turned out that we knew the same people, connected across decades and across the world. And we had learned different things from the
Wow.
same person. And it's just such a small community that we get to be part of as scientists.
Yeah, no, the international science community is so international and so colleague to colleague. Every country. It's pretty neat
The
to have
politics
these
changes,
connections.
but people are the same everywhere.
Yeah, yeah, yeah. It's really
So,
good.
okay, this has been amazing. We have shared out your link for Carleton University. I hope that you get to travel sooner than later with safety.
Yes, I
And
hope for all of us that we get to resume more normal lives.
I'm happy in my house. I'm not going to lie. Me and my introverted self are quite pleased, but I do normally get to go and give talks around the world, and I'm missing that. And I'm going to miss that income as well, not going to lie. Um,
Yes.
it's weird.
It is a
Life is
very weird
weird.
time. Yeah.
But thank you for spending some time with us. Um, I'm going to go ahead, switch our screen over to showing chat, and enjoy your new kitchen office.
Thank you. Thank you. Thank you, Pamela. It's been a pleasure. Bye, everybody.
Bye bye. Um, Thank you, everyone, for being here with me all this day while we have brought you the Daily Space. We have brought you the NASA Town Hall. We have brought you Paul Burns, Richard Ernst, and explored the science of Venus, which gets way too little attention. This is going to round out our streaming for today. We will be back tomorrow morning at 10 a.m. Eastern with morning coffee. Tomorrow it's my turn to, well, share my lack of joy with 9 a.m. with you as we go through and review all that is new and needs highlighting in space and astronomy. My name is Dr. Pamela Gay, and I have been your host. Also, today you have seen Annie Wilson, who did morning coffee, and We're a team. We are a product of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. This episode will be produced by Susie Murph, and we are here thanks to the generous contributions of people like you. Your bits, your subs, your patronage at patreon.com/CosmoQuestX is what keeps us going. And we're going to be here through all the weirdness of our current world to keep you going. Together, we can do anything. So if you want to suggest someone I should raid, we will keep the science flowing. But for now, I am going to say, wherever you are in the world, have a fabulous morning, evening, or afternoon, and wash your hands. Bye-bye, everyone. All right, so they can't hear you or I, but they can hear me. Thank you so much. I hope you enjoyed that, and I really enjoyed getting to pick your brain. Cool. Thank you. It's pass it on to others. We're gonna keep doing streams like this, as long as we can. I'm glad. All right. I will see you later. Have a wonderful day. Bye-bye. Yeah, and we will get you the link.